Welcome to the IEEE webinar on executing final year B.Tech projects and report writing. I am Dinesh Gopinath, member of faculty in Electrical Engineering Department, College of Engineering, Trivandrum. I thank IEEE Kerala section for this opportunity to interact with the young IEEE members through this webinar. As we know, people choose to do projects in a variety of topics. And while it is very difficult to guide on individual topic of possible final year projects, there are some common precautions and preparations that can be taken to reduce the hardships involved. I will elaborate a few guidelines that would make it easy for you to wrap up your final year project and present a meaningful report. This year it is particularly challenging for the B.Tech final year students in Kerala on account of the last days of instruction in the colleges due to COVID-19 scare. Those who depend exclusively on the campus laboratory facilities may be facing an issue of access to the resources. I hope we can come out of this very soon and focus on the projects. Let us look at the three areas that we are going to cover today. One is simulations. The second one is on building hardware, some issues. And third is on the report writing. Most of the undergraduate projects now have a simulation components. Sometimes it is acceptable to have a complete simulation project too if done properly. Mostly people choose MATLAB Simulink combination as the simulation tool. However, many of us may not have access to MATLAB licenses. Those who are not having access to MATLAB can use Scilab Xcos combination, which is a free alternative to MATLAB without any licensing issues. However, if your college provides a MATLAB license, it would be great. MATLAB is basically a scientific engineering programming language, and Simulink is its visual simulation tool extensively suitable for nonlinear system simulation. It has now enhanced capabilities to simulate circuits also, just like SPICE based circuit simulators. We choose MATLAB Simulink mainly for system simulation and control design simulations, and in order to do it effectively and quickly, most of the times we will adopt idealized models, but you can always include non-idealities into your model. Only thing is that it will make it more complex and somewhat more time will be taken for simulation, and sometimes you need more computational power also. Simulink's advanced libraries have models for most of the subsystems components used in electrical engineering and other branches of engineering. But if they are not accessible due to any licensing restrictions, we can also build our own models from the basic Simulink building blocks like summers, gains, integrators, selector switches, etc. After MATLAB, another popular tool is SPICE. This is a circuit simulation tool which is based on component SPICE models. In order to build a circuit model, we need to have models of each of the components. It is also possible to write SPICE models based on the components' input-output relationships and physics-based equations. Most of the component manufacturers also supply SPICE models of their components. There are other simulation tools like PSIM, Sabre, PSCAD, ETAP, etc., most of which are circuit-oriented tools. PSCAD and ETAP are exclusively used for power system analysis and simulation. PSIM is popular with power electronics engineers. When using simulation tools, a few things must be kept in mind, like solver algorithm, what kind of solver algorithm that we choose, what is the step size that we choose, what are the error tolerances that we expect or set in our simulation. Accuracy of simulation and speed of simulation are two things on either ends of the spectrum as concerning simulation. If we try to achieve speed, accuracy may be compromised, and otherwise speed and memory utilization may be compromised. This is true for all kinds of simulators. Basically, most of the power electronic systems belong to a special category known as stiff systems. These are systems which have multiple time constants which are far apart. Like in a motor drive, for example, the smallest time period involved may be the switching time of the switches, and the largest may be the electromechanical time constant of the motor. Such systems require particular care while simulating. Most of the undergraduate students with less exposure to simulation techniques are likely to use the default settings in MATLAB. So an example is shown here with a converter simulation in order to see the effects of settings on the simulation outcome. Okay, so I have invoked MATLAB here, and I have also have built a simulation model for a boost converter, a simple boost converter which converts a voltage from a low voltage DC to a high voltage DC. So if you look at this, I have created these models based on non-ideal elements. If you look at the inductor here, you can see that there is a series resistance which represents the winding resistance. Similarly, for the capacitance, there is a series resistance which represents the equivalent series resistance or ESR of the capacitor. So you can also model it in an ideal manner, but I would like to know the effects of those non-ideal elements in the performance, so it is better to include those. So here you can see the this is an open, see that it is an open loop simulation. Here I am changing the duty ratio from minimum duty ratio to a maximum duty ratio at 150 milliseconds. Inside this PWM block, we have a triangular carrier getting compared with a duty cycle signal to produce the PWM waveform. And you can also see that there is a continuous, there is a power GUI block kept here, which is required for some simulation models built using the Simscape power system block set components. So now if you go back to the MATLAB command window and editor, here I have a MATLAB script which initializes all the variables in the model. So if you look back here, you can see that there is D minimum here, D minimum here, D maximum here, and the resistance RL, L, everything is defined here as variables, not numbers here. So those variables will be initialized in the script here. So the advantage of going for this approach is that you just have to run this script once and all the parameters in the model will be initialized at once. And having a script like this is having another advantage where you can include the design calculations also within the script. So that is what I have done here. I have made the basic design calculations in the script itself. So that calculates the inductance value, capacitance value, everything required. So now go back to the model here, and now you go to this tab modeling. This interface is applicable to the latest version of MATLAB. There may be slight changes in older versions of MATLAB. So if you go to the model settings here, a configuration parameters window will open here, which sets the basic parameters for the simulation. So by default, it will be the solver type. Solver will be selected as variable step, and the solver will be automatically selected, and the maximum step size is also selected automatically. So this is how it looks like when it is when this simulation settings window is opened by default. Okay, so let us go to that default settings and then try to run the simulation. So here, if you run the simulation, you can see the progress here. It will take some time. Yeah, so please look at the progress here on the bottom side. So it is finished. Now let us look at the waveforms by invoking the scope. You can see that some waveforms are here, but this is not right. Okay, this is not right because I have some experience with this kind of converters. We can easily see that this is not coming out properly. So if you zoom these waveforms here, during some portion the waveforms looks okay, but once you increase the due ratio, you can see that there are a lot of issues here. Okay, so this now let us change the simulation configuration parameters from variable step size to here I'll change the maximum step size here to 1 microsecond. So here what I have done is I have chosen the maximum step size here at least 1/50th of this the minimum time involved in the model. So in our case, the model is that of a boost converter which switches at 20 kilohertz. So its time period will be 1 by 20 into 10 raised to 3. So I'll take a time which is at least 1 by 50th of that. So here I am choosing 1 microsecond here, and let us see what happens with these settings. Click simulation. Now you can see that it is taking some more time than the earlier case. The earlier case we just had to wait only a few seconds. Now it is taking more time to finish the simulation. So we'll wait for the simulation and see the results. Okay, now if you see, we have waveforms as expected. You see the inductor current waveform, the capacitor output voltage with ripple here, the output current ripple, the switch voltage, everything we can see here. This is as expected, even though this does not include many of the effects of non-idealities which we have neglected in the model. So if you want those effects to be included, your model would become more elaborate. Okay, so similarly you can try try with fixed step simulation also. So if you go to the simulation configuration parameter dialog box and choose the solver as a fixed step solver, and here you can see a lot of solvers are available. You can choose any one of these. Only thing is that if you are choosing a higher order algorithm, the result will be more accurate in general, and it will take more time to simulate. And if you are going for a lower order algorithm, it will be faster, but it may be of having very low accuracy also. Some of the lower order methods like ODE1 may cause instability also. I mean, the simulation may diverge, the solution may not converge, and it may diverge. So that is the effect of the numerical algorithm going into unstable region. So if you are going to have a fixed variable step simulation, you can see that there are some of the algorithms which shows within bracket stiff as the parameter, as the peculiarity. So that means they are suitable for heavily stiff systems. But in our case, this is a fairly small system, and it is not that much stiff, even though it is a power electronic converter. But there are more complex systems which may require these simulation algorithms. So you'll have to try your simulation with different algorithms and different maximum step sizes, and compare their results before you conclude that the result is correct. Okay. Okay, so now we will look at the other kinds of simulators, basically spice based simulators. Some of the examples of these are LT Spice, OrCAD, ngSpice, etc. ngSpice is an open source and free version of Spice. OrCAD is a commercial one, and LT Spice is a proprietary but free spice based simulator which is widely used by the industry. So one problem that may occur in spice based simulations is that at times there could be convergence errors which happen due to the inherent limitations of the algorithms used for computation. There are some tweaks you may try if you are facing an issue. So an example of spice based simulation I will show using LT Spice. LT Spice is a freely available spice simulator which can be downloaded from Analog Devices website. So I have invoked LT Spice here. LT Spice is a software available for Windows and Mac. Let us open a schematic which I have already done. This is again a boost converter converting from 100 voltage to a larger voltage. So here you can see that the schematic is drawn here. Here you have the component dialog box here. You can select the components from these libraries and place it here, and you can use the wires from here and connect these components using wires, and you can label the net using this icon over here. You can give these names. So I have given the net names as different nodes have been named. This is named as Vout, this is named as vSwitch, and so on, and this is the PWM signal. So here Instead of drawing a complete circuit for the generation of gate pulse and gate drive circuit, I am using a very simplified model for the gate drive portion. So I am using just a simple resistance as the for limiting the maximum gate current to the MOSFET. I'm creating a control voltage. This control voltage is the is a simple DC source. I'm putting the value at 0.5. This 0.5 will mean 50% duty ratio, and I'm using what is called a behavioral voltage source. This is available in the component library as BV here. Okay, this is a behavioral voltage source. This means that the output of this voltage source can be defined as a function of some other voltage or current in anywhere in this circuit. Okay, so you can see that I am using a ramp here. A ramp is designed using a pulse generator with rise time and some definite rise time and zero fall time. So I'm basically modifying the pulse into a ramp and create the ramp. Here is the comparison voltage. Basically you are comparing this DC voltage with the ramp to generate the PWM. So the PWM modulator is designed using a behavioral voltage source. So you take a behavioral voltage source, you can see that this is B1 here and this is V3 here. V is for normal voltage source and B is for behavioral voltage source. And I have defined the output of that behavioral source as PWM, and I am defining this voltage as so if you right click, you can see that there is a value and I am giving an equation there. This is a fairly easy to understand syntax here. So this voltage is equal to, if the voltage at V control, that is this one, is greater than the voltage at V ramp, then the output is 15 volt, otherwise it is 0. So that means as long as the voltage, this control voltage is greater than the ramp, it will give a pulse output here. So that is how this is implemented. Now let us see these settings here. You can see that a control panel is invoked. There are a lot of parameters you can change here. You can see the solver here also. Compared to MATLAB, there are only 3 solvers here, because for circuit simulators, basically the number of algorithms that can be successfully applied is limited. So so here we have trapezoidal, modified trapezoidal and gear. If you are not getting good results, or if your simulation is not converging, you can try changing these, and also you can try changing these numbers. Okay, so it is out of the scope of this webinar to go into the details of this, but thing is that you have opportunities to tweak with the settings of the simulation here also. Okay, and now you can see that here there is a spice directive here, which is introduced by this this button here, and this spice directive tells what kind of simulation you have to do. There is a transient analysis that is possible, AC analysis is possible, DC sweep analysis is possible, noise analysis is possible, and DC small signal transfer function and DC operating point, all these are possible. So we are using a transient analysis here, and initial time, final time, and the step size can be given here as also. So now let us save this and run the simulation by clicking this icon here, run. So suddenly one window opens. So now if you want to see the inductor current, you place the mouse over the inductor, a current probe will appear, and if you click there it will show the current. So now let us zoom this waveform. You can see the inductor current as expected. Similarly, the output voltage also you can see the output voltage. Now you can see that what you can see is here is output voltage is settling to a voltage 200 volt here, which is, if you zoom you can see the ripple in that. Okay, so here you can see that I am using an ideal capacitor here. So here also, if you want to include a ESR, you can add a resistance in series with this and study the change. Okay, so this kind of simulation is useful when you design circuits. If you want to see the voltage stress, current stress, the loss in the circuit, okay, you can plot the current and the voltage, and then you can go here, you can add a trace, and you can write an expression here which is basically a multiplication of two variables. Like for example the voltage across the switch is V switch here, V switch multiplied by I switch. I switch may not be directly available here. So yeah, that is ID, that is the drain current of MOSFET. So this red color waveform is basically the power in the switch. So if you remove other waveforms, make only power waveform here. So this is the instantaneous power here. Okay, so this is having very high peaks because of the reverse recovery currents in the diodes. So let us look at the diode current here. You can see that diode current is having peaks because of reverse recovery. So because of that you have peak power here. So if you take the average of this power, then you can get the average switching the power lost in the MOSFET. Similarly, you can study the power lost in the diode, in the inductor, and so on. So you can find an efficiency analysis from this. In order to find the average power of this power waveform, you will have to conduct an FFT over this. Okay, that provision is also available here. You can see the LT Spice manual and online resources for to know how to do that. Okay, in the case of simulators, it is important to take all possible observations by changing different parameters and studying the effects in not only the primary target outcome like the output voltage or output power or output current, but also on the intermediate variables. For example, in a power supply simulation, some of the variables that are of interest are voltages across the devices, switches, and current through the various components, outputs of controllers, and things like that. Okay, so here doing a simulation is basically like running an experiment. So you will have to change the control variables. For example, in the previous simulation you can see that I've changed the duty ratio and studied the result. If it is a closed loop system, you can study the controller performance by introducing changes in the load or changes in the input voltage and so on, and study how the dynamics of the system evolves. Okay, so in this simulation, the details are of importance. The numbers are important because the numbers will tell you whether it is meaningful or not. Okay, So for example, variation of some parameter like load resistance, input voltage, controller gain, bandwidth, etc. When they change, you can study the results. Okay. So if the numbers are not making sense, for example, if the currents or voltages observed are huge values or very minuscule values, we can conclude that there is some problem somewhere in the simulation setting or in the model itself. So you will have to look at that issue further and then correct it. Okay. Now, when it comes to hardware development, I have shortlisted popular projects under 3 categories. There are, of course, other types as well, like instrumentation projects, software projects, power system based projects, and so on. But most of the undergraduate projects in electrical engineering today tend to use some kind of embedded controller, and as you all know, the most popular ones are the Arduino boards. So there are popular projects like using other microcontrollers having several features like Wi-Fi, for example ESP8266, Raspberry Pi, and so many other controllers. Then there are IoT projects. So this talk is not a tutorial on any such projects. However, I would like to say that if you're doing a project using such controller platforms, you'll have to write the code yourself rather than copying from the internet. Most of the projects, such projects fall into system integration type, where modules are already available and ideas, even code, is available readily. All that you have to do is put everything together. In my opinion, such a integration alone cannot be counted as a good B.Tech project, because there is no hands-on experience as far as the students are concerned. Of course, unless if you are doing everything from scratch, you code it and you design the hardware, you do a custom design all by yourself, then it is good, of course. If your project contains an embedded controller which does only rudimentary on-off control, then it is basically a simple implementation. In order to add value to such projects, you may think of extending the utility by collecting data from the sensors and doing some data analytics and a suitable software interface. Power electronics type projects have sufficient challenges to be addressed in it. PE projects include design and fabrication of converters as power supplies, inverters for motor drives like EVs, battery chargers, wireless chargers, DC to DC converters for solar PV systems, and so on. Now, coming to the mechanical fabrication intensive projects, building something complex as complex as an electric vehicle is a highly capital and time intensive task, and unless sufficient funding is not available, it is better to focus on subsystems that are realizable and that can make up an EV probably as a later project. Okay, maybe the integration can be done by your juniors or so. So as the size of the system increases, the engineering challenges also change. Remember, EV projects done in a scaled down fashion is like, for example, if you're saying that if your project is an EV electric vehicle and you're building a very small cart over a tabletop and tell that is your EV, then that is having not much value, because the challenges involving building a real EV prototype are totally different from building a small scale down toy level vehicle. Okay, of course, if you are planning more complex things like autonomous vehicle or its algorithm for path discovery and navigation, then such small models are valid, because you are spending more effort on the algorithm side and the software side. Okay. Now, those of you who are working on hardware projects would have already started working on the prototype. If you have finalized your design and components, the time is running out for procurement of components. If you have not yet done that, then it is going to be a tough time. Some of the components are to be brought online from international vendors, which take definite time to arrive at your location. Especially in the present scenario, it may take more time for freight and transportation. And while you're waiting for the components, you may finish the design of the PCBs, the printed circuit boards. But the question is, do you really need a PCB? That depends on your hardware scale and hardware circuit. A project hardware should be feasible, reliable, and a cost-effective circuit. Circuits that are handling small currents and voltages can be reliably operated even if they are built on a breadboard and are wired well. The proof of concept can also be done in a breadboard. However, if the circuit involves very high frequency switching, and then the parasitic inductances of the wires and the parasitic capacitances present between conducting points may cause unexpected behavior. This is true for higher power handling converters also. If the signals being handled are of low frequencies, typically 1 to 10 kilohertz, and if power level is not that much, breadboards should be fine. Otherwise, you may have to go for a proper PCB. In power converter projects, if the switching is higher than 10 kilohertz, it is better to go for a properly designed PCB. If the circuit is not a complicated one, you may consider even a general purpose PCB to do the job. Fabricating circuit in a general purpose PCB is time consuming, but you can save time on the PCB design process. For practical PCB design, there are free as well as commercially available software. Depending on availability, you may opt for software like Eagle, KiCad, OrCAD Layout, Altium, etc. When making a prototype, if the circuit is tested, and bugs are corrected, you may think of presenting your prototype in a neat way. It could be either open or closed. You may adopt an open type prototype where the wiring, connectors, PCBs, contactors, and relays, etc. are mounted on a flat board, usually Hilum sheet or thin MDF board. Otherwise, you may also house your prototype inside an enclosure, plastic or sheet metal based one, depending on your budget. Metal housing is good for power electronic converters as they would provide shielding. However, at the moment you are putting your converter or prototype in an enclosure, the thermal behavior is going to change. For power circuits, this could be a problem. So for power converter projects, proper heat sinking of the devices is essential, and if needed, additional fan cooling may be provided. So please refer to the thermal design sections described in power electronics textbooks for understanding and designing heat sinks for power devices. There are connectors available in different shapes and sizes and with different voltage and current ratings. Okay, so when you select a connector, you must look, for example, if we look at the connectors, different types of connectors. You can see different types of connectors here. There is Phoenix connectors, there are connectors with lugs and so on. So many types of connectors. So you'll have to choose connectors judiciously based on your requirements. And when you select a connector, you have to look at its voltage and current ratings, their data sheets, ensure that they are suitable for the voltage and current ratings of your application. And be careful if you are dealing with high voltages. If you are dealing with high voltages, you must provide enough distance between conducting points, known as creepage distance. And finally, you may need some auxiliary power supplies and powering for powering the control circuit or subsystems in your prototype. You can select cheap linear regulator based design or SMPS based power supplies from the market, or you can make them yourself, which of course is a more difficult task. If you cannot afford to buy extra power supplies, you may provide enough connectors in the board for receiving power from lab power supplies. But be aware of the isolation requirements of power supplies. So what do you mean by isolation of power supplies? For example, let us consider a case with a DC-DC converter which is having two switches like this, one top switch and one bottom switch here. Okay, so this is the DC supply. Now we have to give a gate pulse here at the gate of this switch T1 with respect to its source here. So this is S1 here, and you have to give a pulse here, which is of course complementary of the top switch pulse, to the gate of T2 with respect to the source of T2. Okay, now if you are having a gate drive signal here which is having a ground, and let us say two gate pulses are coming out of it, G1 and G2. So if you are connecting from G1 to G1 here, and in order to give the gate signal with respect to the ground, we'll have to connect this source to the ground. Similarly, you connect G2 here and S2 here. Now you can easily see that S1 and S2 are connected to the same ground. That means this point and this point are electrically the same. So that means you are basically bypassing this transistor, and when you turn on the top transistor, you will be short circuiting the DC supply. This is a very dangerous situation. So what you have to do is you will have to have a gate pulse for the top switch and the bottom switch in a totally isolated manner. There are different techniques for this. You can use opto-isolator based design, you can use pulse transformer based design, or you can use what is called as a bootstrap based gate drive, like the one used in the IC IR2110. So in these cases, for example, if you are using an opto-isolator based power supply, then gate drive supply, then your gate pulse will be given to the LED part of the pulse from the controller will be given to the LED part of the opto-isolator, and the output can be taken from the collector of the transistor part. So here you will get the output, and this power supply here is having a different ground than the input side. So that means these 2 points are totally isolated electrically. So you use one such circuit for the top switch, another such circuit for the bottom switch. So though the S1 and S2 will be totally different points, they will be isolated. So if you are using power supplies for the top gate drive circuit and for the bottom gate drive circuit, then their grounds must be isolated. So this is one thing which you will have to remember. So when we use auxiliary power supplies, you will have to see whether they are isolated or non-isolated as per the requirements. Now some tips while developing the hardware. You will have to provide decoupling or bypass capacitors near to the VCC pin of ICs and subsystem boards, and they are typically an electrolytic capacitor or tantalum capacitor in the range of 1 to 10 microfarad, and a ceramic disc or a multi-layer ceramic capacitor, which are basically available in SMD form. The value can be 0.1 microfarad. These two different types of capacitors must be connected in parallel, and they should be physically placed very near to the supply voltage pins. Now, while designing PCBs, care must be taken to avoid 90-degree bends in the tracks. Also, we will have to choose track widths as per the current capacity needed. When prototyping, whether it is in PCBs or in breadboards or general purpose PCBs, always use shorter wires and leads of components to avoid issues due to parasitic inductances. And don't forget to provide test points for crucial signals. And of course, as I told earlier, be aware of the creepage distance in high voltage circuits. While testing your prototypes, make observations of all crucial signals in a good digital storage oscilloscope, because of course DSO is the norm now. If possible, avoid taking photographs of the screen. Instead, you can use the export facility available in most of the modern oscilloscope. Export the waveform as a comma-separated variable file, CSV file, which you can later import into MATLAB or a spreadsheet program like Excel and plot the waveform. Or you can export in a JPG format via the USB drive usually available in the oscilloscope. Learn how to do this from the oscilloscope manuals. However, if this facility is not available, then of course you can take a photo. But when you take a photo, try to take the photo at the level of the screen, showing the complete screen in the frame, and use a tripod to avoid shake. And all volt per division, time per division, all other settings, probe, multiplication factor, everything should be visible. To highlight parameters like time period, and so you can also use cursor measurements available in the oscilloscopes. Now, if dynamic results like change of voltage with load, change of speed when the motor is loaded, etc., can be captured using a single shot mode available in the oscilloscope. Just like in the case of simulations, make detailed observations like peak-to-peak ripple voltage, overshoots across switching devices, etc., if permitted by the bandwidth of the scope. Very narrow oscillations or ringing on the edges of the switching waveforms can be caught in only high bandwidth oscilloscopes. But most of the entry level oscilloscopes are having at least a bandwidth of 20 to 50 megahertz, so that should be enough for this purpose. Now, while probing, take precautions to avoid dangerous situations. For non-isolated channel scopes, always connect both or all the probe grounds to the same point. Now, If the line voltage powers the circuit, then always isolate the DSO power or isolate your circuit using an isolation transformer. Now why this is required is because just as I mentioned the case of gate drive circuit and why isolation is required in such a circuit, most of the power electronic circuits are having floating voltages, like some points in the circuit may be swinging to either a high voltage or a ground level voltage, depending on the status of the switching device, on or off. Now in non-isolated oscilloscope, both the grounds of the oscilloscopes are the same point. Now let me explain that with the help of a drawing. For example, let us take the oscilloscope. Let us assume that the oscilloscope is here and we have two channels, say channel 1 and channel 2, and the middle point is the probe and the outer point is the ground. So this is ground and this is also ground. And suppose we are probing a circuit like this, a bridge circuit, something like this. So suppose you are probing the channel 1, connecting the channel 1 probe and connecting it here to see the voltage across this device, say D1, and for that you will connect the ground here. Okay, now this channel, if you are connecting across output voltage, you want to know the output voltage, then you will connect this point here. Now what is the problem? The anode of this diode D1 is connected to ground, and the load, one end of the load is also connected to ground. So basically this point and this point are electrically the same, they are shorted. So you are altering the circuit and it may cause short circuit also. So this is also a very dangerous situation here. So in most cases the supply voltage is also one end may be grounded, so this will get interfere with this scope. So if you are having this kind of setup, it is better to connect both the grounds of the channels to the same point and then use the other probe to connect to the devices. Of course you will have to isolate the oscilloscope, either the oscilloscope or your circuit here, using an isolation transformer. Otherwise you can use a isolated channel scope. Isolated channel scopes are now available. Okay, now what is output of a project? Many people are getting obsessed with output. We are not getting output. Some people are worried if they are not getting output, but in my opinion it's always outcome versus output. Outcome is more important than the output. Outcome of a project is that the learning part of it. If you're going through so many issues, that means you're going through a lot of learning opportunities. So you should focus more on that, and then outputs will follow suit. If your steps are all okay, then your output also will be okay. So try to figure out what has gone wrong, and of course that requires detailed observations, as I told earlier. So from detailed observation we can get to figure out what has gone wrong. Okay, now we come to the last portion. This is the report writing. So it is better to go for a approved template approved by your university or institute. Most of the universities provide template. If not, you can create templates from other universities, changing the templates of other universities, and you can create template. There are word based templates, there are LaTeX templates, etc. are available, and I will now show you a sample template which you can which is a LaTeX template. There is a cloud based service called Overleaf, and it offers a free account. So if you sign into Overleaf, you can create a LaTeX project here. So I'll show you a project template, which is a modified version of a B.Tech project report. This Overleaf based, or the cloud based Overleaf service, is a collaborative one. That means many people can work on the same document. Different students or their students and the guide, all of them can work together. Okay, there is a review option available. So on the left pane you have the LaTeX code, on the right pane you have the PDF document. So again, this is not a LaTeX tutorial. I'm just showing that such a thing is possible. Even without installing LaTeX in your laptop or PC, you can use a cloud-based service. And I'll share the this right now. I'll share it, this template. You can view this template. So I'll show this. Here. Okay, so this is the link for that template. You can make a copy and you can edit in that. Okay, so the main structure of that report would be, if you go back and see the report there, you can see that there is an abstract, there is a introduction chapter. Let me just zoom this. Okay, there is an introduction, there is a literature review, and there is a chapter on the proposed system. You can combine, if some chapters are very small, you can combine them and make a single chapter. So the third chapter here is the details the proposed system. Fourth chapter describes the methodology, what is the design methodology adopted, how you're attacking this problem. And the fifth chapter is on system design, or you can even combine the methodology and design chapters into one. And then results and discussion, and then finally conclusion and future scope, and finally the references will come. So that is the structure of a typical B.Tech project report. In the abstract, you will have to write a very concise summary of the work, a very concise summary which starts from the context of the work, the background of the work, and why you have chosen this and what you have done, and finally a hint on the conclusions or results. That will be the structure of the abstract. Okay, and if you look at this file, you will get to know the structure in detail. Okay, now let us come back to this. So when you use reporting, one popular tool among B.Tech students now is Fritzig. What is that? Fritzig is a tool to generate graphical representation of a circuit, the physical representation of the circuit. Instead of showing a circuit diagram, it shows the actual board, like the Arduino board, and connections as physical wires. Please do not use Fritzig pictures as circuit diagrams. They are not professional circuit diagrams. That is not the way in which engineers draw circuit diagrams. And in fact, engineers find it somewhat difficult to trace the Fritzig circuit, especially if it is very complex, and understand and interpret the circuit quickly. Instead, if it is a well-drawn circuit diagram, the engineers can quickly read and understand it. So as engineering students, you should focus on professional circuit diagrams rather than hobbyist kind of methods like Fritzig pictures. Now when you want to draw pictures or figures, you can use scalable vector graphic tools or SVG tools like Inkscape, Microsoft Visio, etc. Of course, it requires some practice, but the output quality will be very good. And if you are having circuits, those circuits can be drawn using circuit schematic tools like KiCad, OrCAD Capture, or the schematic tool of Eagle, etc. You can, if it is a very large circuit, you can create the split it into different pages and include that in your report. Now when you import simulation graphs, every detail in the graph should be very visible, very clear and visible, like the x-axis data, the y-axis data, the labels on the x and y-axis, and the legends. All those things should be very clearly visible. If the default figures, for example in MATLAB, if the default figures are not good enough or having very small size, you will have to increase the font size and introduce boldness to the fonts and so on in order to make them legible and clear in your report. Okay, people reading your report should be able to understand quickly what you are displaying. And always acknowledge the sources through citations. And of course, if you go back and see, I think I have yes, so here you'll have to acknowledge the sources and avoid plagiarism. Do not copy anything from the web or from any other report. Plagiarism is a serious academic offense, and in fact your university may be asking you to give a certificate to the effect that you have not done any plagiarism in your report. So write everything on your own in your own language, and if you want to write about some idea in your report which is done by others, then acknowledge those sources. If you are reproducing a figure from a paper or from the internet, give acknowledgement, give the source link as a reference, and behind the as the figure caption, you please include the figure source. And as electrical engineers, we use IEEE style for citations. If you look at the IEEE citations, I'll show you in the For example, the references will be as appearing in the IEEE papers. Like there is a particular format, each punctuation mark has value, so please look at standard IEEE journals and use that method. And within the text you will use the citations as square brackets, so those numbers in the references will appear within square brackets. So for example, see here, here. So this is how the citations are made in IEEE journals. And okay, as summary, we have gone through some guidelines for simulation, hardware design and reporting, and I hope this would be useful for finishing your final year B.Tech projects. Thank you very much for listening.